Hi, everybody. It's Professor Mitchell. We are finally finishing up Chapter 7 today on decimals, percents, and real numbers. And today we're going to talk about real numbers. In this section, you'll be able to understand and explain real numbers, operations on real numbers, nth root, and in particular square root, how a to the power 1 over n and a to the power m over n are defined and why they're defined this way. And finally, expressions involving radicals and radical exponents. Every rational number can be expressed as either a terminating decimal or a repeating decimal. It was the ancient Greeks who discovered numbers that are non-terminating and non-repeating decimals. Such numbers are called irrational numbers. Characteristics of irrational numbers: there must be an infinite number of non-zero digits to the right of the decimal point, and there cannot be a repeating block of digits. So irrational numbers occur in the study of area. Remember that the area of a square is calculated using the formula A equals S squared. If S equals 11, then the area is 11 squared, which is 121. Conversely, if we know the area, we can calculate the length of a side of the square. For example, if the area of the square is 49, then the length of a side is given by the formula S squared equals 49. Now, that equation has two solutions, 7 and -7. However, lengths are always non-negative, so 7 is the only possible solution. Now, I want to clarify that so far we have not run into any irrational numbers, but we're getting there. First, let's talk about square root a little bit. A square root of a non-negative number a is a number x such that x squared equals a. So the way I like to say it is, how should I say this? If this, the square root of a number, let's talk about a specific number, 100, all right? The square root of 100 would be, I'm thinking of a mystery number that when I square that number, I get 100, okay? Now there are two numbers that do that, 10 and -10. However, if we just want to talk about the positive square root, that's called the principal square root. And I just noticed it is spelled correctly here and not over here. It's interesting that they spelled it two different ways. This is the correct way right here. If a is any non-negative number, the principal square root of a, which is written like this, and you've seen this before, is the non-negative number x, such that x squared equals a. So in the example I was just talking about, the principal square root of 100 would be 10. Just 10. All right, so in this example, we're first going to find the square roots of 144. So a square root is any number whose square is 144. So there would be two numbers that do that. Those would be 12 and -12. However, the principal square root of 144 would just be 12. And then to find the square root of a fraction like 4/9, again, I'm thinking of a mystery number that when I square it, I get 4/9. Well, that would be another fraction. The numerator of that fraction would have to be 2, and the denominator would have to be 3. And remember, this is only going to have one answer. This is talking about the principal square root. So the principal square root of 4/9 is 2/3. And to make that a little bit more general, we can talk about other roots. The nth root of x is written like this. We were just talking about square roots. Square roots could be called second roots, all right? They're never called that, but that's the idea. If n is even, and by the way, this number n is called the index of the radical. If n is even and x is positive, then the principal nth root of x is positive. And I think you really need an example here, so let me get out my pen. So for example, to talk about the fourth root of 16, that would be a mystery number that when I raise it to the fourth power, I get 16. All right, and this would be, so there would technically be two of those if we were talking about the fourth roots of 16. But when we use this symbol, oops, we're only talking about the positive one, so that would be 2. Okay. Now, if n is even and x is negative, then the nth root of x is not a real number. So, for example, the fourth root of, well, negative 16. And the reason this would not be a real number is because it is not possible to raise any number to the fourth, any real number to the fourth power and get a negative number. Any real number to the fourth power is going to be positive, or at worst, it's going to be 0. Okay, so this would not be a real number. I keep losing track of my mouse. There we go. And then if n is odd and x is negative, then the nth root of x is negative. So an example of that would be, let's say, the cube root or third root of negative 27. So I'm looking for a real number that when I raise it to the third power, I get negative 27. So because this exponent is odd, it is possible for an odd power to be negative. Okay? And in fact, this happens when the mystery number being cubed is negative 3. All right, so let me just, let's see, change to a different color here real quick. Okay, because the number that goes in this blank is negative 3, that means the cube root of negative 27 is negative 3. Okay, and then finally, let me point out at the bottom, it's tempting to say that the square root of a squared is always a. However, that doesn't work when a is negative, right? For example, if I take the square root of the square of negative 5, the square of negative 5 is 25, right? If you have the negative 5 in parentheses like that. And of course, the square root of 25 is 5. All right, and 5 is the absolute value of negative 5. So if you don't know, especially when you don't know whether your number a is positive or negative, you have to say that the square root of a squared is the absolute value of a. Okay, so there's a fair amount to take in there. Hopefully you've seen this before. All right, let's move on. All right, irrationality of square roots and other roots. Some square roots are rational. For example, the square root of 49 is just 7. The square root of 100 is 10. However, other square roots, like the square root of 2, are irrational. All right, so I'm going to show you a really, really cool proof that the square root of 2 is irrational. And I see that my animations are messed up here a little bit, but this stuff will fill itself in. So we're going to show that the square root of 2 is irrational using an indirect reasoning proof. So the way that works is we start off by supposing that there is a rational number, which I could then write a over b, such that the square of a over b equals 2. So then this number a over b would be the square root of 2. Okay, so let's go with that. The square of a over b is a squared over b squared. That's one of our exponent properties from back in, gosh, when was that? Chapter 2 or something. A squared over b squared would have to equal 2. And now multiplying both sides of this equation by b squared, I would get a squared equals 2b squared. Okay. By the fundamental theorem of arithmetic, remember that about prime factorizations? Because these two numbers are the same, a squared and 2b squared, then their prime factorizations have to be the same. The fundamental theorem of arithmetic said that every whole number has a unique prime factorization. So these two numbers, a squared and 2b squared, have to have the same prime factorization. In particular, the prime number 2 has to appear the same number of times in the prime factorization of a squared as it does in the prime factorization of 2b squared. Okay, it's a little hard to see where this is going, but we're actually almost there. Because b squared is equal to b times b, no matter how many times 2 appears in the prime factorization of b, it has to appear twice as many times in b times b. So suppose for a second that part of the prime factorization of b was 2 to the 5th, okay? Then the prime factorization of b squared would have to include 2 to the 10th, okay? Think about that. A squared also would have to have an even number of 2's for the same reason that b squared does, okay? So in the prime factorization of a squared, the number 2 has an even exponent, and in the prime factorization of b squared, 2 has an even exponent. But that's going to be a problem because we just got through saying that a squared has to equal 2b squared. So as soon as we multiply b squared by 2, so let's say that in the prime factorization of b squared, 2 appears to the power 8, okay? So when you multiply b squared by 2, then the prime factorization of 2b squared, 2 would have to be raised to the power 9 because you just threw in an extra factor of 2. So in the prime factorization of 2b squared, you would have an odd number of 2's. And that's going to be a problem because we just said that the number of factors of 2 in a squared had to be even. But now in the prime factorization of 2b squared, the number of 2's has to be odd. So that is a contradiction. And the contradiction could have only been caused by the assumption that the square root of 2 is a rational number, that it could be written as a fraction a over b. All right, so because of that contradiction, that must mean that the square root of 2 is an irrational number. Okay. Now, if that seems a little confusing, it's perfectly natural, all right? Something that you may have to think about for a little bit. Okay. The geometric interpretation of irrational numbers. This figure shows a segment 1 unit long, constructed perpendicular to a number line at point P. Thus, two sides of the triangle shown are each 1 unit long. All right, so this side of the triangle is 1 unit long. This side of the triangle is 1 unit long. So by the Pythagorean theorem, remember the Pythagorean theorem, a squared plus b squared equals c squared. That would have to mean that the length of the hypotenuse is the square root of 2. So now if you swing this side of the triangle down to meet the number line, this point Q corresponds with the square root of 2. And if you ask your calculator, the square root of 2 is approximately equal to 1.414, and then I think it goes to 136 or something. And you can see in the picture, Q is not quite halfway from 1 to 2, so that makes sense. By the way, you're going to be doing a lot more of this kind of thing in Math 20B. Other square roots can be constructed as shown in this figure. I think this is kind of cool. So here's the triangle we were just looking at with the two sides equal to 1 and the hypotenuse square root of 2. If you build another triangle on top of that, with a leg whose length is 1, then the hypotenuse is the square root of 3, which is also an irrational number. If you do it again, you get a hypotenuse that's the square root of 4, which is just 2. That's not irrational. But then it keeps going like that. We know that the square root of 2 is between 1 and 2. To obtain a closer approximation of the square root of 2, you can squeeze the square root of 2 between two numbers that are between 1 and 2. So for example, we can figure out that the square of 1.4 is 1.96, and the square of 1.5 is 2.25, and that must mean that the square root of 2 is between 1.4 and 1.5. All right, so now let's talk about real numbers. The set of real numbers R is the union of the set of rational numbers. Remember, those are numbers that can be written as fractions, and the set of irrational numbers. So the union of rational numbers and irrational numbers gives you the set of real numbers. The decimal form of any real number is either terminating, repeating, or non-repeating, like the square root of 2, or pi is another example of an irrational number. Every integer is a rational number, right? For example, take the number -7, that's an integer. You can write it as -7/1, that makes it rational. And so every rational number is automatically also a real number. So every integer is a real number, and every rational number is a real number, but not every real number is rational. For example, the square root of 2 is a number that's real, but is not rational. So this kind of shows the relationship between all the different sets of numbers that we've talked about over the whole semester. So the biggest set is real numbers, the set of all x such that x is any decimal. That is split between irrational numbers, decimals that neither terminate nor repeat, and rational numbers, numbers that can be written as fractions. Okay, remember, numbers that can be written as fractions will always either repeat or terminate. Now, inside of the set of rational numbers, you have integers. So integers are a subset of rational numbers. Whole numbers are a subset of integers, and natural numbers are a subset of whole numbers. So biggest sets are at the top, smallest sets are at the bottom. All right, real numbers have basically all of the same properties that we've talked about for other sets of numbers. For example, real numbers have the closure properties. If A and B are real numbers, then A plus B and A times B are unique real numbers. Commutative properties, if A and B are real numbers, then A plus B equals B plus A, and A times B equals B times A. And you have the associative properties for addition and multiplication. You also have the identity property. 0 is a real number. So the number 0 is the unique additive identity. And the number 1, which is also a real number, is the unique multiplicative identity. And remember, that just means we're talking about a number that when you do that operation with that number, you just wind up with the same answer. So A plus 0 is always A times 1 is always A. And you have inverse properties within real numbers. For every real number A, the number opposite A is its unique additive inverse. When you add those two numbers together, you get 0. And then for every non-zero real number A, 1 over A is its unique multiplicative inverse. So it still only works for all numbers except 0. 0 never has a multiplicative inverse. You have the distributive property of multiplication over addition and subtraction. You know how that works. And you still have the multiplication property of 0. Any number times 0 equals 0. And just like with rational numbers, and actually irrational numbers too, we never talked about that, for every real number a and b, there is always another real number in between those two. All right, now we're on to rational exponents. If x is a real number and n is a positive integer and m is any integer, then x to the power 1 over n is equal to the nth root of x, as long as the nth root of x is a defined real number. That's what they mean by meaningful. Okay? And then x to the power m over n is equal to the nth root of x to the m. And there's actually another way you can do this. You can also think of it as the nth root of x, do that first, and then raise that number to the power m. It's equal to either one of those things as long as the nth root of x to the power m is a defined real number. Okay. All right, let's see. It can be shown that the properties of integer exponents also hold for rational exponents. So the product rule, the quotient rule, the power to a power rule, all that stuff works for rational exponents just like it did for integer exponents. These properties are equivalent to the corresponding properties of radicals if the expressions involving the radicals are meaningful. In other words, as long as the radicals are defined real numbers. All right, so let's simplify each of these, starting with 16 to the power 1/4. So 1/4 power means 4th root. Okay. Oh, okay. Yeah, that's a different way to do it. I didn't think about doing it this way. You can rewrite 16 as 2 to the 4th, and then by properties of exponents, the 4 and the 1/4 cancel each other out and just leave you with 2. All right, but I will mention, you know, if you understand 4th roots, this is kind of forcing you to figure out the 4th root of 16 anyway. You have to come up with that too. All right, but the 16 to the 1/4 means the 4th root of 16, which is 2. All right, next we have 16 to the power 5/4. So let's see, how did they do that? Oh, okay, so they're breaking the 5/4 power into 1/4 times 5. We just figured out that 16 to the 1/4 is 2. And then 2 to the 5th power is 32. Next we have -8 to the power 1/3. So that would be the cube root of -8, which is -2. Next we have 125 to the power -4/3. Remember, negative exponent means reciprocal. So what we can do with this one is rewrite the 125 as 5 to the 3rd. 3 times -4/3 is -4. And from back in chapter 2, we know that 5 to the -4 means 1 over 5 to the 4th. So that would be 1 over 625. And then finally, we have the 1/4 power of -16. And that is not a real number because, let's see, did we talk about this exact example earlier? I think we might have. The 1/4 power of -16 would mean the 4th root of -16. So that would be a mystery real number whose 4th power is -16. But when you raise the 4th power of any real number, you get a positive number, or worst case, you get 0. You would never get -16. So since there is no real number whose fourth power is -16. The 1/4 power of -16 is not a real number. All right, and I believe that's going to do it for section 7.5, and that's going to do it for chapter 7. So we'll